is precalc, guys. What we're doing is I'm finishing all of the log stuff together, which for the properties of logs and how to deal with logs and how to solve with logs, I'm going to put together in a 4-3-4-4 packet here. So we're putting it all together. 4.5 is using logs and solving equations, but it's the word problem stuff. So we'll go back to the book for that because they have a lot of problems that we can handle there. So today we're going to talk about how to expand and condense logs using the laws of logs and the change of base. So the first thing up here is you guys should have seen this last year for sure. You may have even seen this in Algebra 2, but I'm not sure if we get that far. So last year you guys would have been introduced to logs. You probably hated it, probably didn't like it very much, but then you realized that logs are just exponents, and if they follow some simple rules. Think back to your exponents. If they have the same base, what can you do to exponents? Add them. If they have the same base and you're dividing them, you subtract the exponents. Okay, and so on, or you multiply. That's what these rules are. Because a log is an exponent, if we have log base b, and I did change this again from the way your book is set up. I use b for the base, and not an a. So log base b of 2 numbers, or 3 numbers, or 20 numbers being multiplied together, you could separate them to their own log of the same base, the base that was original, okay, by addition. If you're dividing the numbers inside, you could separate them to their own with a subtraction sign. You subtract the logs. And the last one is if there's a power on an individual piece, once you get that piece by itself, you can actually take the exponent and move it out front. So it's the exponent times the log of that number. There are proofs for all 3 of these in your book. You guys should have actually done them hopefully last year. I'm going to spare you guys the proofs, but I would say it's a good read. Look through those proofs. It kind of helps solidify these and why they work. So, the logarithm of a product of numbers is the sum of the logarithms of the numbers. Putting everything to words there. You can read the rest of those. So, we're going to use those laws on the last page. Now, I'm going to give you guys a hint here. We need to expand these. We want to expand because when we expand, we can also simplify at times using some of the rules that we had gotten from the other lesson. And so, I like to equate this to either going on a car trip and getting to your destination or getting ready to leave. Okay? Right now, we are all inside the car. There's our car, the log base x. Okay? And so, my rule, I know at my house is, especially with the younger kids who want to take everything with them out of their bedroom, with them anywhere they go, is whatever you put in the car, you need to take out of the car. And so this is what it is. You have a suitcase, you have a bag full of toys, or whatever they are. You need to take it out when we get there. So expanding is like you got to your destination, you now have to grab all of your stuff to leave. And so what it means is that going back to our last slide, I got 6 times x, which means I should be able to unpack both of them into their own. They take all of their stuff. So would you guys agree that this would be log base x of 6, and then what? Plus log base x of x. At this point, we could be done, but we also can simplify this. Using one of our properties from before, how many people recognize that log base x of 6 is done? But log base x of x is not. What can happen with the log base x of x? The bases are the same, so they cancel each other out, and you're left with log base x of 6 plus 1. So that one's pretty much done. So that one wasn't too bad about getting to the destination and everybody kind of branching out on their own with their stuff. The next one is going to highlight that a little bit more. Now the next one is natural log. It doesn't have a base, guys. What's going on? Yeah, it's e. We don't need to write it, right? It's assumed. Now, another cool thing about this is that you notice that there's not just two numbers and we got ones that are multiplied on top and we got something on the bottom. It's the natural log of AB divided by the cubed root of C. Here's a cool thing. Things in the numerator get added. Things on the denominator get subtracted because you're dividing. So when you multiply on top, you add. If you're on the bottom, you will subtract. So in this case, it becomes natural log of A plus natural log of B minus natural log of cubed root of C. Now, going back to that whole traveling thing, A and B really didn't bring too much with them. They just kind of brought themselves, right? But the cubed root of C actually brought some extra luggage. I can actually unpack that a little bit more. Cubed root is really the same thing as what? 1/3 power. So I'm going to convert that. Natural log of A, natural log of B, minus natural log of C to the 1/3. Now that they're all individuals, the individual will unpack themselves. So that means this 1/3 needs to go to the front. So natural log of A plus natural log of B minus 1/3 natural log of C, and you're done. So the rule is everybody has to get out of the car first, and then once they're out of the car, they will unpack individually. So let's go back to our rules. That means the top two rules go first, and then you can apply the third rule or law when expanding. When we condense, which means go from the right side to the left side, you actually work in reverse order. So now we're getting ready to go on that trip. And if you're going to get ready to go on the trip, you expect everybody to pack on their own before everybody getting in the car, right? It'd be kind of silly to get in the car and then say, okay guys, let's pack. It doesn't work that way. So we're going to get to that in a second, but we're going to use some of these rules, and I guess we are going to condense a little bit here, but I want you to evaluate using those rules. Let me see if I can make this a little bit larger. So what we need to do is we have log base 4 of 2 plus log base 4 of 32. So just evaluate. So somebody's like, oh, no, not a big deal. I don't know what this log is, so I'm going to set it equal to x. Is that okay? Could I say then that this is 4 to the x equals 2? Would you guys be okay with that? We did that in our homework the other day. And you'd be like, oh, that's 1/2. That log is equal to 1/2. But then I do the same thing over here with log base 4 of 32. And now you're like, 4 to the x equals 32. Now you're stuck. Because I really don't know a power on 4 that's going to get me to 32. Now again, we're going to get to stuff that we can actually solve that by getting the same base tomorrow. But we can make this easier for ourselves. We can go back up to the beginning and say, hey, wait a minute. That's a log base 4 plus another log base 4. If I'm adding two logs together with the same base, I can do what with their numbers? I can multiply them in a single log. So what if I did that instead? 2 times 32, which is log base 4 of 64. and now go through that process of saying, hey, I don't know what you are, you're an x for now. 4 to the x equals 64. Wait a minute, x has to be, what is it? 3. So it equals 3. Right, a little faster. So you look at part B, I don't know if 80 or 5 work that way like we did here. So I think I'm just going to apply the rules first, right? The laws. And the law here said, hey, they're the same base, but you're subtracting. What should I do? Divide. So 80 over 5, which is log base 2 of 16. And we're going to simplify this. So again, I'm going to arbitrarily set it equal to x so I can actually switch it. So see if it does equal something nice. That's 2 to the x equals 16. And you would say the answer is 4. So to simplify that expression, it's a fancy way of saying 4. So let's flip the situation and let's go take the trip. Now you can see that we have lots of things being added and subtracted together. So we got 3 natural log of s plus 1/2 natural log of t minus 4 natural log of the quantity t squared plus 1. What we need to do now is write this as one single log. Basically, we're all getting into the same car. To do this, we got to work on that list from the bottom up. We need to go to rule number 3, law number 3, and say individuals need to pick up their own stuff. So that means each one, in this case, has something to pick up, right? Now, it's not always going to happen. But our first step would be to do that. So natural log of s cubed plus natural log of t to the 1/2. Now, this is where you have options. One option is to keep the negative there and just bring a 4. Okay? The other option is going to be natural log of s cubed plus natural log of t to the 1/2. And then instead, I'm going to take the negative 4 and bring it up. Do you think there's going to be a difference in the end? There will not be a difference in the end. So, we now have it, so it's all the same log base being added or subtracted. The cool thing about it is, if you add the logs, you do what to their numbers? You multiply. When you subtract their logs, you divide. So it doesn't matter how many there are. The ones added go to the top. The ones subtracted go to the bottom. So this becomes natural log of s cubed t to the 1/2 over t squared plus 1 to the 4th power. The one thing I probably would do with this problem would be simplify your expressions back to where you can, instead of half powers, put them as square roots. But I don't think it's going to be, let's just do that. But you should recognize that 1/2 power is a square root. There's not much of a difference, but it's just easier so you don't get your things mixed up. And notice that if you had square root of t first and then s cubed, it doesn't matter. So this is the answer. But how does this one become that? Well, let's change colors so I can show that. Again, hey look, this time they're all added. So that means they all go to the top. I'm going to change that to square root of t right away. And then it becomes t squared plus 1 to the negative 4. But wait a minute. If they're all multiplied, guys, and one of them has a negative exponent, where should that negative exponent go? To the bottom. So you would eventually have to bring it to the basement anyways to make it a positive exponent. So therefore, they are the same. The next thing is the change of base formula. I did change this one slightly from the way the book has it as well, because I use log base b of x instead of a. But your calculators, guys, are very limited. They only do base 10 or base e. Not every problem you're going to come across, or the real world, does not just revolve around 2 logs. And so they found out that you can actually take the log of any numbers with bases of anything as long as you use the formula. So the formula is log base b of x is the same thing as log base a, any a, bigger than 0, of x over log base a of b. So now the x goes to the top and the base number is still on the bottom, but it becomes a regular number. That means I can change a log to any other log I want by using the change of base. But here's the thing. Looking at our examples below, log base 8 of 5, if I wanted to find the actual value of that, I'm not going to change it to log base 2 or log base 17 or 26. I'm going to change it to a log base that I can use or I have. Which 2 log bases do I have? Log base 10 and log base e. So, guys, instead of writing it log base a over x and log base a over b, I'm just going to do log x over log b, which is log base 10. But here's the thing. I could also use log base e or natural log of x over natural log of b. They also both work. We're going to demonstrate that on our problem below. So why is this important? Again, we'll go back to this whole idea that I don't know what it is, so I'll just arbitrarily call it x. So maybe I could switch it to exponential to figure it out. So that's 8 to the x equals 5. Does anybody know the power on 8 that'll give you 5? Well, first of all, is it bigger than 1? Because 8 to the first power is 8. It's already bigger than... So you know that a value has to be less than 1, bigger than 0. But that doesn't help us necessarily give us a number. Maybe it'll help you guess and check. But instead, what I'm going to do is I'm going to do log of 5 divided by log of 8. Take your calculator out, and what do you get? Point 7 something, 774? 774. Hey guys, just for fun, do the natural log of 5 over the natural log of 8. I changed the base to e instead of 10. What do you get? It's the same. It doesn't matter. That's the cool thing about it. Log base 9 of 20. 9 to what power is 20? Bigger than 1, but less than 2. So, you need to do log of 20 over log of 9, or natural log of 20 over natural log of 9. A little bit easier to write natural log. When you guys get to calculus and stuff, they're probably most likely use natural logs versus logs. Now, the question came up before is, what happens if we can't solve it, right? Like we did. It's not solvable here. It would not be solvable here. Now we have this way to figure out a number. Guys, 0.774 is an approximation. Anybody who put on their calculator, it continued on. So we got approximations. We have exact solutions. or exact solutions. So if it asks for the exact solution or value of log base 8 of 5, you can easily place in log of 5 over log of 8, natural log of 5 over natural log of 8. That would be an exact solution. 0.774 is an approximation. So be careful when you're using it, what you're using it for. It's always better to use the exact number when doing your calculations than approximations, right? The longer you can hold out using something like this, the better. So almost at the very, very end, you would actually give the approximation as you're going through your steps. But your work should support your answer. Any questions to that? I've got one more thing to show you before I hand out the worksheets. Okay. One of the worksheets has a problem like this. It also has problems that set equal to a number instead of another log. Then you just have to switch to exponential. That's how we do those. Guys, in this case, if you had a log base anything of some number equaling a log of the same base of another number, the only way for these two logs to ever be the same is if the numbers inside are the same. Okay? So in this case, I can basically drop the logs and say, when does 3x minus 11 equal x minus 3? Sometimes this results in a linear problem like this. Sometimes it results in a quadratic. You have to then solve it using all those techniques. Be careful. Check your answers. You can't take a log of a negative number, I think it is. So be careful. So you get 2x equals 8, x equals 4. Check it. Does it work? Okay. So your homework, I'm going to hand out the worksheets, is their worksheet size 3 and 4. So it's the jokes that say something about a bar, and then there's a joke that says something about a vampire. Yes. So have a great day.